Hello, Team Mobius, and welcome to the latest installment of Tech Tuesday. I'm Carl Copeland, the founder of Mobius Aero and the inventor of the Verso motor. This is the motor that we're designing for our electric race plane. And today I would like to start a new series on the basic concepts of motor design. And when I say basic, I do mean basic. I'm going to try to keep this very simple and very clear, plain English. I'm going to do my best to avoid a lot of jargon and acronyms to the best of my ability. And I want to keep this simple and straightforward because I feel like to most people, electricity and magnetism are a mysterious concept and a mysterious force that they don't understand, and they don't even believe. A lot of people I speak to don't even believe they can understand it, but that's not true. I believe that it just needs to be simply and clearly explained. And once put into the right frame and context, it is actually quite an easy concept to understand. So I believe all of us are familiar with magnets, and they're quite a bit of fun to play with, especially when you're trying to force two similar poles together and the way they repel each other. But whether they repel or they attract, we're familiar with that. In fact, there's a wonderful children's toy that I've been caught stealing from toddlers that you're seeing here on the screen now that clearly illustrates these principles where when you have poles lined up where the north pole of one magnet is facing the north pole of the other and the two souths are facing, then they push apart. And when you line them up in series where the positive and the negative or the north and south poles are touching, just like lining up the batteries when you're putting them into the remote, then they all attract to one another and stick tightly together. So when building a motor, we're using those two principles. They're the magnet's ability to attract and a magnet's ability to repel. And in fact, this simple motor diagram here really reveals that process. So another interesting fact about magnets is that the force we use to describe it is actually electromagnetism. And that is because electricity and magnetism are the same force. They just have different expressions of that force. And to simplify that into a very crude parable, it's the same thing with water. So, water is a molecule, H2O, and depending on the temperature state of water, you either have steam, liquid water, or ice. But they're all water. They're all the same molecule. They just express themselves differently based on the conditions that they're in. So electromagnetism is the same way generally. It's not the best analogy, but it helps you understand the concept that when this force is expressing itself with attraction and repulsion, it's doing so as magnetism. And then when you have electric flow through a wire or you get static shock when you walk up to and touch the doorknob, that's the electricity side of it. But they're really the same force expressed differently. And in fact, looking at this simple diagram of the motor, what you're seeing is you're seeing two permanent magnets, a north magnet and a south magnet, and you're seeing in the center of that magnet a rotor that's made out of a copper wire. And that's because when you put electricity through the copper wire, you turn that wire into a magnet. It's an electromagnet using electromagnetism. And so, what I love about this diagram is it really does show the really most basic principles of how a motor works. And that is that you have one magnet that's either attracting or repelling against another magnet. And we do so in such a way where we're causing it to push around an axis or, a shaft, and it rotates. And we're using that push and pull to create the rotational force. So when you're designing a motor for a specific job, there are three basic parameters you need to establish from the beginning. The first one is, what is the work that's to be done? So this work is usually expressed with horsepower or kilowatts. And it's really not too relevant which one of those you use, because they in essence use the same properties to determine that net sum. To help you understand uh, how that works, let's take kilowatts because it's the most direct. It doesn't have any weird constants you have to divide by or anything. So it really is, what is a watt? A watt is the voltage times the current or amperage. That's just two different words for the same thing. And so voltage is the same thing as pressure in a water system. So if you have water flowing through a pipe, the pressure, the water pressure on that line coming from the water tower, well, that's the same force as voltage, which also happens to be in a combustion engine or other electric motor. It's also expressed as speed. So whether you're talking about speed, when I speak about speed, when I'm talking about RPM, or the rotations per minute. And so the speed of the motor, or the voltage of the electricity, or the pressure of the water, that is all the same factor. And then on the other side, you have, so if you've got voltage, you have current. And in the horsepower analogy, you have torque. So current, torque, and in the water analogy, gallons per minute. Those are all the same other side of that force. So you have speed times torque, volts times amps or current, and water pressure times flow rate, gallons per minute. All that's decided by the size of the pipe and the pressure of the water, or the size of the wire and the voltage you're applying. So I probably said that in too many revolutions, but hopefully you grasped what I was saying. And so you want to know what the work is that needs to be done, and that work gets divided into those two categories. And for the sake of horsepower, we'll go back because that's an easier concept to understand. So you have to know, what's the torque requirement? Like how much force do I have to apply to move whatever it is I'm trying to move? And then the speed side, how fast do I have to move it? And so those are the first two principles. What's the work to be done? The second parameter you need to know is, what's the space that's available for this motor? How big can I make the motor in order to get the job done? And the reason that's important is because it plays into how much leverage you have. So the longer your crowbar, the more leverage you have to get a job done. Same thing applies with the motor. The bigger you can make the motor, the easier it is for that motor to have a leverage advantage and get that work done. And then the third parameter you need to know is, what is the power source? How am I powering this motor? So again, just like with the work to be done, I need to know what's the horsepower, what's the speed and torque I need to deliver. You also have to know what's the voltage and current I need to put into the motor to get that work done. And so work to be done, available space for the motor, and the power source. Those are the three parameters you start with. Thank you guys so much for tuning in to this Tech Tuesday, part one of Motor Design Basics, and I'm looking forward to our next installment.